Welcome, my dear friends of the elegant algorithm. So this is already the second to last of our 12 lectures in discrete optimization this year. And in this lecture, we are going to treat two absolute classics from the area of approximation algorithms. So still under the umbrella of coping with NP hard optimization problems. The first one is going to be an algorithm on the set cover problem. And as a special case, we will start with a vertex cover problem. And the second one is going to be an algorithm for the notorious traveling salesman problem. And that is maybe the most beautiful and most elegant of all approximation algorithms. Very simple and just beautiful. And as a start, we are going to come back to the vertex cover problem that we already discussed in the last lecture extensively. Okay, so let me first remind you what the vertex cover problem actually is. So we are given a graph, an undirected graph, and have to select a subset of the vertices, here this blue subset of vertices, such that all the edges of the graph are covered by these vertices. So that means for any edge in the graph, I have to select in blue at least one of the two endpoints. And in the last lecture, it was quite a bit of work to show that the greedy algorithm is a logarithmic approximation algorithm. So always computes a vertex cover, which is at most a factor log n away from the optimum solution. And the greedy algorithm was the one that always picks vertices of maximum degree next. Now, that is the problem and our result. And the general challenge that we have in the design of approximation algorithms is the following. So let's say we talk about minimization problems. Okay, so what we want is a polynomial time algorithm A, which on any instance achieves a solution value A of I, which is at most alpha times opt of I, where opt of I is the optimum solution value. The trouble is we do not know the optimum solution, hence we do not know the optimum solution value in general. And if you remember in the analysis of the greedy algorithm here, we had this one particular step where we could relate the next selected vertex in some way to the size of the optimum solution. And that was why we could achieve or prove this performance guarantee. That was a bit complicated, and in general, that is also difficult to relate to optimum solution values, which we don't know. So what is usually much, much simpler is to work with lower bounds instead. So we are talking about the minimization problem. So what we typically need in order to get a good approximation algorithm is a good lower bound, LB of I, on the optimum solution value. Because if we can show that our algorithm is at most alpha times this lower bound, because the lower bound is a lower bound on the optimum solution value, we are in shape, because then our algorithm achieves a value which is at most alpha times the optimum solution value. So depicted here, the optimum solution value would be here. This would be the mysterious lower bound that we try to find and hopefully can compute. And we prove theoretically that our algorithm is not worse than alpha times this lower bound, which is of course not worse than alpha times the optimum solution, right? So that's the way to go. And let us see how we can do that for the vertex cover problem. So what is the mysterious lower bound that we can work with? And we already know a lower bound, which is inspired by the corresponding dual problem, which is the matching problem. So the algorithm works as follows. We start with an empty vertex cover. And as long as there are edges left to be covered, I pick an edge, not a vertex now, but I pick an edge from V to W, say. And to cover this edge, we would have to select at least one of the two endpoints, V or W, but we're actually selecting both. And then we eliminate both selected vertices and all the incident edges from the graph and iterate the whole procedure until everything is covered. And because we are selecting edges and then eliminate all the incident edges, the next edge will be disjoint from all the previous edges. So effectively what we compute is an inclusion maximal matching in the graph, a set of edges which are disjoint from each other. Obviously, This algorithm will have a linear computation time if we implement it carefully. But let's first look at an example to see that the algorithm is clear. So here's a very simple graph. And what the algorithm is doing, it selects edges, not vertices now. So it selects, say, this first edge and both incident endpoints. Then everything that is covered is deleted from the current graph, and we are left with these two edges here. And then again, we select another edge, say this one, and both endpoints. And then everything is covered, and we stop, right? Now, the claim is that this simple algorithm already achieves a much better approximation guarantee than the greedy algorithm, even though less intuitive. So on any graph, the algorithm is at most gives a solution value, a vertex cover, which is at most twice the optimum solution value for the vertex cover problem. And as I said, the trick is to work with a lower bound on the optimum solution value, which in this case is given by a matching, right? So the claim here is that the optimum solution value, and actually the solution value of any feasible vertex cover, is at least as large as the size of any matching in the graph. Okay, so the size of any matching in the graph, once again, is a lower bound on the size of any vertex cover. That should be clear if you look at this example, for instance, when I have independent matching edges which are disjoint from each other, I know that I have to select at least one of the two endpoints for both, right? So that is a matching of size 2, and I will have to select at least 2 vertices in order to cover these edges. And if I have a matching of size 10, the same, I will have to select at least 10 vertices in a vertex cover. So that is the lower bound that we can work with. And now the edges that are selected by the algorithm, they are an inclusion maximal matching. Inclusion maximal because we continue until everything is covered. Okay, let's call this matching MA, the matching edges selected by the algorithm. It's by inclusion maximality that we know this will constitute a solution to the vertex cover problem because we iterate as long as there is edges uncovered and we select both endpoints, right? So the inclusion maximality of that matching makes sure that our solution is indeed a vertex cover. Now, our algorithm selects both endpoints of the selected matching edges. So the number of vertices that the algorithm selects, that's twice the number of edges that the algorithm has selected. These matching edges, that's a matching, is a lower bound on the optimum solution value, so a lower bound on the size of any vertex cover. So therefore, I get as a performance guarantee exactly the same too, right? So the algorithm's vertex cover is at most twice the optimum solution value, and that's already the end of the proof. So indeed, even though the algorithm is a bit less intuitive in the sense that when I have an edge and I select an edge, I select both endpoints, even though to cover this particular edge, I would have to select only one of them. This algorithm gives a much better approximation ratio than the greedy algorithm from the last lecture, and the whole analysis is also much, much simpler. So that is also the message: working with lower bounds can simplify life considerably and sometimes even give much better performance guarantees. Just as a side remark, this algorithm has also an instance, or there exist instances where this approximation ratio of 2 is actually achieved. So the analysis is tight in the sense that there exist problem instances where the algorithm is also not better than twice the optimum solution. And you already see the example here. If the graph is just an independent set of edges, the algorithm would select all of them and always select both endpoints, and then we would have twice the necessary vertices selected in comparison to the optimum solution. And this simple algorithm is actually one example of a so-called primal dual approximation algorithm. In the following sense, we compute a primal feasible solution, in this case a vertex cover, and along with that, we also compute a dual feasible solution, which is namely a solution to the matching problem. And the fact that we have weak duality and the size of any matching is a lower bound on the size of any vertex cover, that helps us enormously in order to set up a very simple analysis to prove a very good performance guarantee here. And that can be generalized. So let me try to make this primal dual idea a bit more explicit, and first, once again, for the vertex cover problem. Okay, so what I set up here is an integer programming formulation of the vertex cover problem. So we have 0, 1 variables xv for selecting or non-selecting the vertex v. We minimize the total number of selected vertices, and the only constraints are that for each of the edges, right, for each of the edges we have to select at least one of the two incident vertices. Now, if I forget about the integrality constraints for a moment, in the corresponding dual, I actually will have dual variables for each of the constraints, right? So there will be a variable ye for each of the edges of the graph. The objective function in the dual will be a vector of all ones. So the dual will be a maximization problem where I maximize the sum of all these ye variables here. So maximize number of selected edges subject to which constraints? Well, the corresponding dual constraints will be that for each of the vertices of the graph, I can select at most one. So that's precisely the matching formulation. Okay, so first of all, forgetting about integrality, that is the corresponding linear programming duals of each other. And with integrality, we see that the matching problem, that's the integer dual of the vertex cover problem. So what have we been doing in this algorithm conceptually? So let's say we started with formulating our vertex cover problem as an integer program, and then set up the corresponding linear programming relaxation, right? So where we relax the integrality constraints to non-negativity constraints. Remember, we don't need to set up an upper bound constraints because we're talking about a minimization problem anyhow. So that constraint will be redundant. And then we can also write down the corresponding dual of this linear programming problem. We can do that not only for the vertex cover problem, we can in principle do that for any problem that we have formulated as an integer programming problem. And the crucial idea is the following, namely that any feasible solution of the dual of this linear programming relaxation, so any feasible solution of this red linear programming problem is a lower bound on the optimum solution value for the integer program. Okay, and the algorithm was exploiting the fact that any matching in the graph is a feasible solution in this dual, right? Any matching fulfills all the constraints in this dual, so it's a feasible, not necessarily an optimal solution for this dual. But any feasible solution of this LP dual is good enough to provide a lower bound for this primal integer problem here. Why is that? Well, because any solution of this LP dual, that's a maximization problem, is a lower bound for any solution of this LP primal. And this one is again a lower bound on this integral version of the problem, because this is the less constrained problem. Okay. And also notice a little warning here that, of course, I mean, this is two LP duals of each other, and the optimum values of these LP duals will coincide, but the optimum solution values of these LPs do not necessarily correspond to feasible solutions for the integer problem. So we know that already. We know there is a special case, a special class of graphs where this is actually the case, namely where we only have integer optimal solutions, and that was bipartite graphs. So for bipartite graphs, the corresponding polytope described by these inequalities here is an integer polytope, so has integer vertices only. So that would indeed correspond to feasible vertex covers. And the corresponding polytope described in the dual also has integer vertices only, and that corresponds to matchings. And the fact that primal and dual have the same objective function value, that was Koenig's theorem saying that for bipartite graphs, the size of a minimal vertex cover, that would be an optimal solution here, is equal to the size of a maximal matching in this bipartite graph. But for non-bipartite graphs, this is not necessarily true, because if you think about this little triangle graph here, we have optimal solution values achieved when all the vertices are selected with a value 1/2 in this LP relaxation, giving an optimum solution value of 3/2. And in the dual also we would select all the edges with value 1/2, giving the same objective function value 3/2, but then it does not correspond to a feasible solution to the vertex cover problem. However, since we do not go for optimality, we only want to design approximation algorithms, any feasible solution of this LP dual is good enough as a lower bound, right? So once again, if I depict that here on the real line, that would be the optimum solution value of the vertex cover problem. That would be the optimum solution value of the corresponding linear relaxation, right? Which could be different. For example, here for non-bipartite graphs, it is actually different. And then by linear programming duality, that is also the optimum solution value for the corresponding dual here. And any feasible solution of this dual maximization problem will lie here, right? And a feasible or a matching was a feasible solution to this linear programming problem here. And now this is a general idea for the design of approximation algorithms, right? Start out with an integer programming formulation of the problem. Look at the LP relaxations, try to find feasible solutions of the dual of the LP relaxation. And now the tricky part is to relate the feasible solutions of this dual, in our case it was matchings, to feasible solutions of the primal. But if I am able to relate these two with each other, then I can prove approximation guarantees. So once again, as a brief summary, so for a minimization problem, any feasible solution for the dual of the LP relaxation of the problem gives me a lower bound on the optimum solution value. And the challenge or the trick is that we have to come up with feasible solutions for the primal, vertex cover problem was that, and feasible solutions for the dual, which we are kind of proof are close enough to each other. And vertex cover matching, that was this factor of 2. Okay, so here for vertex cover, we compute a vertex cover X, that was the primal feasible solution, and we compute a feasible solution for the dual Y, such that they are exactly a factor 2 away from each other. And then by duality theory, we immediately get the performance, the corresponding performance guarantee of 2. So here is again a picture that hopefully makes that glass clear. So this is the unknown optimum solution to the vertex cover problem. And what we are doing in the algorithm, we are computing a matching M, which is a lower bound for the optimum solution value, a matching M, and a feasible solution X. That was the vertex cover by selecting both endpoints each time, which are precisely a factor of 2 away from each other. Because we are computing a feasible vertex cover, that gives us that the solution value of the vertex cover, so twice the size of the matching, lies here. And of course, the fact that this value is a factor 2 away from this lower bound M here also shows that the solution that we compute is within this range, so at most a factor 2 away from the optimum solution value. Well, and now one of the questions is there a kind of systematic way in order to do that, in order to compute feasible primal solutions and feasible dual solutions which are not too far from each other? And the answer is yes, in principle we can do that. And that would be looking at complementary slackness of linear programs again. So complementary slackness describing optimality of integer linear programming solutions. And now we have to move to an approximate version of complementary slackness. And this would be the idea. So we have a primal linear programming problem, say a minimization problem, and then the corresponding dual is a maximization problem. Weak duality just says that a dual gives us a lower bound, or dual objective value is a lower bound on the primal objective value. That just immediately follows from the set of constraints that we have up here. And we know that we have equality here if and only if these two solutions, these two feasible solutions, x and y, fulfill complementary slackness. And now the idea is, instead of going for equality here, so optimality, we go for something that comes close to equality here. So that means we would have inequalities in the other direction. So we would have a larger equal here and a larger equal also there. So instead of achieving equality, we go for something that I call almost complementary slack. And well, if I have larger or equal here and larger or equal there, I would have equality. So larger or equal up to a certain constant factor. And that would be the idea. So if I have inequalities also in the other direction, then I would get that the objective function value of the primal is at most some factor times y times a times x here, and that one is at most some other factor away from the objective function value of the dual. So that would be corresponding constraints in the other direction here and here up to a certain constant factor. And these constant factors would be these question marks here. So how exactly do we do that? Well, let's just write down or remember what primal and dual complementary slackness means. Okay, so if I have feasible solutions for the primal and dual, x and y, then complementary slackness, primal complementary slackness means whenever a primal variable is strictly larger than 0, then the corresponding dual constraint must be fulfilled with equality, right? Now we are allowing a strict inequality here, but not by too much. So that exactly means that the corresponding, so whenever a primal variable is strictly larger than 0, then the corresponding dual constraint could be strictly smaller than Cj, but not too much. So it's at least Cj divided by some alpha, where alpha is larger or equal than 1. Okay, so it could be not equality, it could be strictly smaller, but not by too much. And we do the same for the dual complementary slackness condition. So whenever there is a dual variable y which is strictly positive, okay, then to achieve optimality, we would have to have equality in the corresponding primal constraint. So again, we allow strictly larger here, but not by too much. So whenever a dual variable is strictly positive, the ith component of a times x is allowed to be larger than the right-hand side bi, but not by too much. So it's at most beta times bi for some other constant, beta. And then if we have two such solutions which are fulfilling these approximate versions of complementary slackness, then I of course still have weak duality, and because I simply have feasible solutions for both primal and dual, but now I also get inequalities in the other direction. Well, not exactly inequalities in the other direction, inequalities up to these two constants, alpha and beta, right? Because now c times x, this c here is at most alpha times y times a, right? So I get c times x at most alpha times y a. And likewise, a times x is at most beta times the right-hand side b. So at the end, I get this factor alpha times beta in this chain of inequalities in the other direction. And indeed, that everything makes sense now, because if alpha is equal to 1 and beta is equal to 1, that would exactly correspond to the usual complementary slackness conditions. And then I would have inequalities exactly in the other direction, and everything here would be equality. Okay. But what we know, if we have a solution that fulfills complementary slackness, then I know that the solution value of the primal that I computed is at most a factor alpha times beta away from the solution value of the dual, and that gives me an approximation guarantee of alpha times beta. Why that? Well, because this is still a lower bound on the optimum solution value, right? So this dual solution value is still a lower bound on the optimum solution value for the prime. So let me summarize now what we did. So if we talk about the combinatorial minimization problem, F being the set of feasible solutions that actually has a formulation as an integer linear program, then the following, this theory kind of describes a recipe of obtaining approximation algorithms. Namely, we have to be able to compute feasible solutions X for all instances of the problem in polynomial time. And if we kind of achieve that we get approximate complementary slackness for such constants alpha and beta here for some solution y of the dual, okay, we only need some feasible solution of the dual. And we compute one feasible solution of the primal and some feasible solution of the dual. Fulfilling these approximate complementary slackness conditions, then we immediately have an alpha times beta approximation algorithm. So let us try to look at that for the vertex cover problem again to make clear how this actually worked there. All right, so what did we do in this algorithm? So whenever, let's look at primal complementary slackness first. So when we select a vertex, a node V, actually in the algorithm we had picked some edge, right? So we had picked some edge F from V to W, and we were selecting both endpoints, okay? Now, whenever, and that is the moment when the primal variable goes from 0 to 1, we are selecting that vertex V. What is the corresponding dual constraint here? Well, the dual constraint, that is the matching constraint. So for all the edges incident with V, among all the edges incident with V, we can only select one of them. So algorithmically, whenever we select a vertex, so whenever we set a primal variable strictly larger than 0, then we do that because we have selected a dual variable to be larger than 0, namely equal to 1, and that was selecting the corresponding edge F, right? So we were actually in the algorithm selecting an edge F, and that means we are selecting the corresponding dual variable YF equal to 1, and that is the moment when the primal variable for this incident vertex V was also set to something larger than 0, namely equal to 1. So what do I mean to say here? Whenever a primal variable is larger than 0, so a node V was selected, then the corresponding dual constraint here for that vertex V is fulfilled with equality. So we have exact complementary slackness on the primal side here, right? Because among all the edges incident with vertex V, here we were selecting one, that is in the dual. So the alpha would be equal to 1 for the vertex cover algorithm. And now let's look at the dual complementary slackness condition. So whenever we are selecting an edge, right, in the algorithm, then actually we were selecting both endpoints, and that is where we only achieve approximate complementary slackness in this dual constraint here. Because the primal constraint for this given edge F that we selected was that we should select at least one of the two endpoints. So, but we are selecting both of them. So in order to achieve exact complementary slackness, we would have to have equality here. Now we allow strictly larger, but we not by too much, only at most a factor 2 larger than this one, this right-hand side here, right? So we have smaller or equal with beta being equal to 2 because we are setting actually both variables xv and xw equal to 1. So the dual constraint is approximately fulfilled with equality up to a factor of 2. Okay, and that means indeed what we already knew, that these two solutions, primal and dual solutions that we are computing with this algorithm, are a factor alpha times beta apart from each other. Alpha was 1, beta was 2, so that gives this performance guarantee of 2. Okay, so now that we have seen that the simple algorithm for vertex cover can be embedded into a more general idea, namely of computing approximately slack primal and dual solutions, let's try to do the same thing at least for one more problem, okay? And that problem is going to be the so-called set cover problem, which is a generalization of the vertex cover problem. Okay, so what is the set cover problem that I would like to attack next? The set cover problem is the following. We are given some ground set E of elements, 1 up to m. That is the elements that should be covered. And these elements should be covered by subsets. So S1 up to Sn, that is subsets of the ground set. And I have to select a collection of these subsets in order to cover all the elements. So if you look down here in blue, these blue dots would be the elements that need to be covered. And in green, you would have subsets that you can use in order to cover these elements. So this is a subset. S1 is a subset that covers elements 1 and 2. S5 is a subset that covers elements 2, 3, 4, and 5. So what is a practical motivation? Somebody was asking for practical motivations of this problem. Well, look at this picture here on the right. That would be a part of a map, a landscape, okay? And then that is kind of partitioned into these grids. And you would like to establish, say, mobile phone connectivity, and you can do so by installing antennas, okay? So you would have, for example, this large antenna number 5 here that you could build at a certain cost, right? And this large antenna number 5, that would be actually covering these cells from the grid. So 2, 3, 4, and 5. And that is exactly this subset S5 that would correspond to the antenna that you are allowed to install or build in order to establish connectivities in these grid cells. And likewise, you would have an antenna number 1 here. That would be one which establishes connectivity in these two cells and so on. So that's exactly the set cover problem. So a subset that I select would correspond to an antenna that I built. Obviously, building antennas costs money. So also in the set cover problem, there are costs attached to the subsets that I can select. And I would like to minimize the total cost of all the subsets that I select in order to cover all the elements. Okay, so now the application has vanished from the slide again, but I would like to find a minimum cost cover of all the elements, of all the grid cells in my vanished picture, such that, minimizing the total cost and covering all the elements, right? So I have to select subsets for each element. At least one subset must be selected that contains it. So in the picture, it says here that there is a set cover S1, S2, S5, and S6, right? If I select S1, these two guys are covered. If I select S2, that is these two guys, 3 and 6. S5 would be those 4 guys, and then there is a leftover, which is exactly covered by S6. So that would be a set cover. And then in general, the objective function is to minimize the total cost of the subsets that I select. And I gave you one example, but the set cover problem is a very universal problem that has a lot of applications, not only in logistics, the example that I just explained, but also, for example, in combinatorial auctions. Now, at some point, I was claiming that the vertex cover problem would be a special case of the set cover problem, or the other way around, set cover generalizes the vertex cover problem. Let's see how we can see that. Because in the vertex cover problem, I'm selecting vertices of the graph, whereas in the set cover problem, I'm selecting subsets. So which subsets correspond to a vertex in the vertex cover problem? Well, in the vertex cover problem, our ground set is the set of edges of the graph, and we are selecting vertices to cover the edges. I only have to reinterpret a vertex that I select by the corresponding edges that it covers, right? So the collection of subsets that I'm allowed to choose in the vertex cover problem, well, that would be the subsets corresponding to the edges incident with a given vertex. So if I select the vertex V in the vertex cover problem, in the set cover terminology, that would mean that I select the corresponding incident edges incident with the vertex V. And then you see immediately that indeed the vertex cover problem is a special case of the set cover problem. And what I would like to do next is to apply this primal dual approach also to the set cover problem. In order to do that, we need one more definition. Well, a given element may appear in a couple of the subsets. So that means that I cover an element by choosing any of the subsets that it contains. And Fe is just how many subsets contain element E. Okay, so that's the number of subsets that contain element E. Let's call that the frequency of an element E in this collection of subsets. And notice that this is exactly 2 for the vertex cover problem, simply because an edge has 2 vertices incident with it. So that is that edge E appears in 2 subsets that I could select. And Fe would be how often an element appears in this collection of subsets, and then F would be the maximum taken over all the elements. So that would be the maximal frequency of any element. Okay, and of course, again, since in the vertex cover element, each element has frequency 2, also the maximum frequency is 2 in the vertex cover problem. Now, since the set cover problem then obviously is a generalization of the vertex cover problem, the idea was to generalize also the primal dual algorithm to the set cover problem. And we do exactly the same thing like we did for the vertex cover problem. So first of all, we set up an integer programming formulation of the problem. So we use variables, xs in this case, because we select subsets S, which are equal to 1 if the corresponding subset S is selected and 0 otherwise. We would like to minimize the total cost of the selected subsets S. What are the constraints? Well, the only constraints that I have is that for each of the elements that need to be covered, I have to select at least one of the subsets that contain this element. So I have to select at least one of the corresponding sets S that contain element E. Therefore, this larger or equal than 1 constraint here. So select one of the Fe many sets that contain element E. Now, just as before with vertex cover, we write down the corresponding linear programming relaxation. So we drop the integrality constraints, and we also write down the corresponding dual of this linear programming relaxation. So in the LP relaxation, we replace integrality by just non-negativity. And once again, because this is a minimization problem, the larger, smaller or equal than 1 constraints are not necessary. Okay, so that would be the fractional formulation of the set cover problem. And here we have the corresponding LP dual. So first of all, what kind of variables do we have? Here at the primal, we have a constraint for each of the elements that needs to be covered. Hence, in the dual, we have a variable ye for each of the elements. And you also see that the right-hand side, the B vector here on the right-hand side is just a vector of 1s. And therefore, the dual, which is going to be a maximization problem, just maximizes the total sum of all these ye's. So in the dual, I select elements, E, fractionally possibly, and the constraint that I have is a constraint for each of the subsets, and it says that, well, if I look at a particular subset S, the elements or how much I take from the elements E in total taken over the whole set S cannot be more than CS, that was the cost of that set S. Okay, so the dual is also known as a so-called set packing problem, but this is not so important now. We select ye fractions ye of elements E, but we are not allowed to overpack any of the sets, so we are not allowed to take more than CS, the cost of that set S, for a given set S. Okay, so all the elements in set S summed up, I can only take at most CS of that. And notice that this Y here is also not constrained to be smaller or equal than 1. So in principle, I could take an element also more than once, as long as it fulfills in total this packing constraint here for the whole set S. Now, for the sake of setting up approximate complementary slackness, let's first look at the regular complementary slackness conditions for this primal dual pair of LPs. So if we have X, a primal feasible solution, and Y, a dual feasible solution, then we have optimal solutions for these linear programs if we have complementary slackness, saying that whenever a primal variable is larger than 0, so selecting a subset S, then the corresponding dual constraint, that was this packing constraint, must be fulfilled with equality. So the original dual constraint was smaller or equal. For optimality, it should be equal. The dual complementary slackness says whenever I select an element E in the dual, so YE is larger than 0, then the corresponding primal constraint must be fulfilled with equality. And the primal constraint was saying originally that I have to select at least one subset S that contains element E for each of the elements. So this was originally a larger or equal than 1 constraint. And then for optimality, it should be equal to 1. And what we are going to do in terms of approximate complementary slackness, we are only relaxing one of the complementary slackness conditions, just again, like in the vertex cover case. Okay, so primal feasibility, as I already said, was a larger or equal than 1 constraint, and we are going to lax dual complementary slackness. So that means we are now, I'm going to describe an algorithm which computes simultaneously primal and dual solutions, X and Y, with the following property, namely primal complementary slackness will always be fulfilled. And for dual complementary slackness, we have an almost fulfillment. So whenever a dual variable is larger than 0, so we are selecting an element in the dual, then the corresponding primal constraint, which was a larger or equal than 1 constraint, may be violated. So I'm probably selecting more than one subset that covers element E, but at most beta many. So for some constant beta, and this beta is going to be the maximum frequency of the elements. So that means in the primal and dual solutions that I construct, an element will be covered by more than one subset, but not too many. So that said, I can describe the algorithm. So as I already indicated, it's going to construct a primal and dual feasible solution at the same time, exactly in the same way like we did it for the vertex cover problem, where we constructed a vertex cover and a matching at the same time. So we start with 0 solutions in the beginning, and as long as there is still an element that still needs to be covered, which is yet uncovered, I choose one of the uncovered elements arbitrarily. And what I want to do, or what I'm going to do, is the following. So we are now going to cover this element E that was selected by at least one subset S that contains it. So XS is going to be set equal to 1. And as I said, we are not going to violate the primal complementary slackness condition. So that means because I'm now selecting a subset S, I'm going to make sure that I fulfill dual complementary slackness exactly. So whenever I now set a set or select a set S, I'm going to make sure that the corresponding dual constraint is fulfilled with equality. And that was the dual packing constraint, which used to be a smaller equal constraint, and I make sure that it's fulfilled with equality. Okay, so how do I do that? Well, remember we choose an element E, and now we do the following. We just increase the corresponding dual variable YE from its current value until I hit one of the constraints, or one of the constraints gets tied for some subset S that contains element E. How do I do that? Well, this element E that I have chosen, that appears in some subsets low. So just for example, say this element E appears in three subsets S1, S2, S3, then somewhere later in the algorithm, I look at the total sum of the YE values for this subset S1. So suppose this is equal to 1, and the constraint that we have to fulfill, it's a smaller equal constraint, says that it should be smaller equal than the cost of that set. Say this is 2 for the first set. Then this element E also appears in the second set S2. The sum of those dual variables, say, is equal to 1.5. Okay, and the corresponding cost of the set is equal to 2. And it appears in the third set, and the sum of the corresponding dual variables YE, say here, is equal to 0.7, and the cost of that set is equal to 1. So then we see that we can increase the corresponding dual variable YE by how much? Well, at most by 0.3, because then we hit this constraint is going to be tight. So if we would increase the corresponding dual variable YE any further than that, we would violate the dual feasibility constraint, and that is something that we don't want. Okay, so we can increase the corresponding dual variable until some of the constraints actually in the dual gets tight. Now it could also be that several, once I have increased this dual variable YE, it could be that several sets get tight simultaneously. And now what I do is for all such sets for which this dual constraint is now tight, okay, so that means fulfilled with equality, I do the following. I select the corresponding set S for which this dual constraint is now tight. And notice that by selection, complementary slackness will be fulfilled because I set this variable equal to 1, so larger to 0, only if the corresponding dual constraint is fulfilled with equality. And of course, once I selected set S or sets S, all these sets that became tight, all the elements contained in these sets will be declared to be covered, so they no longer have to be covered. Okay, note in particular that in this step here, this element E will definitely be covered because at least one set S that contains element E will become tight in this step here, right? So let me again summarize what we have. So whenever we set a primal variable to be larger than 0, so that means here selecting a set S, okay, equal to 1, the corresponding X will be set equal to 1, then the corresponding dual constraint is fulfilled with equality by construction, okay? So hence primal complementary slackness holds, or this approximate alpha will be equal to 1. What happens if I increase a dual variable with a primal constraint? So let's look at dual complementary slackness, where whenever I increase a dual variable larger than 0, what can I say about the corresponding primal constraint? Well, I'm selecting a set, at least one, maybe several sets that became tight for this equality here. So here I'm selecting maybe several sets. How many sets do I select at most? Well, at most as many sets as the frequency of the corresponding element, right? This element appears in a certain number of sets. I cannot select more sets because I'm only selecting sets that contain element E in this step here, okay? So the number of sets that I select whenever I increase this dual variable strictly larger than 0, that will be at most the frequency of the element, and that will be at most the maximum frequency of all the elements. Okay. Now remember what was the original dual constraint. That was originally a larger equal than 1 constraint. We are violating equality here, so it's not going to be equal to 1, but it will be at most f, the maximum frequency. So that means relaxed dual complementary slackness will be fulfilled up to a factor at most f. And that's exactly what we obtain. So f is going to be the approximation guarantee, the approximation factor for this primal dual algorithm. So now we can already finish the complete analysis. Let me summarize that once more for this algorithm. So as long as there is an uncovered element, this algorithm proceeds to cover it, right? We select an element, and that iteration, that element will be covered. So we are producing a feasible set cover. The primal dual algorithm is also a polynomial time algorithm and achieves that computation time m squared times n, where m is the number of elements and n is the number of subsets to select from. How can I see that this is an upper bound on the computation time? Well, I'm covering each of the elements E, and there is m such elements, right? So the algorithm at most has to explicitly consider each of the elements. So that's m many at most. And then for each fixed element, I have to figure out for all subsets that contain that element, and that is at most n many, I have to compute this quantity, namely the maximum amount by which I can increase the corresponding dual variable ye. And that would be this delta here. And that is a summation over all the elements contained in subset S, and that's at most m many, right? So in total, that would be m times n, order m squared n. Okay, so we indeed have a polynomial time algorithm constructing primal and dual solutions in time polynomial. And in principle, we already know by the whole setup of this approximate complementary slackness method that we have an approximation guarantee which should be equal to f. And it's maybe okay to explicitly write down again why this is true. So the value achieved by the primal dual algorithm, well, that's the total cost of all the sets that I selected, right? Now, whenever I select a set S, I know that primal complementary slackness is fulfilled, so the corresponding dual constraint is fulfilled with equality, and that means that this cost coefficient, CS here for set S, is equal to the sum of the corresponding dual variables, right? So I can plug that in for the cost CS because of primal complementary slackness, and I have indeed equality here. All right, now I just reordered the summation. So this was a summation over subsets S and all the elements that contain it, and now I sum it over all the elements and all the subsets that contain that element. So that's the same. And now I can use relaxed dual complementary slackness because I know that for each element E, where we increase the dual variable to something strictly positive, the number of selected sets is at most f, the maximum frequency of any element. So this thing here is at most f, so I get f times the dual objective function value of the LP relaxation, and that smaller or equal comes from the relaxed complementary slackness condition. And of course, this is the solution value of the dual of the LP relaxation, so that is some dual feasible solution, which is a lower bound on the optimum of our original problem, right? Because this dual solution was constructed to be feasible. And that's it. So we have seen two examples, vertex cover and as a generalization set cover, where we can use this primal dual framework to construct approximation algorithms. There is actually more examples, but for the rest of the lecture, I would like to concentrate on the traveling salesman problem and present maybe one of the nicest approximation algorithms of all. Okay, so let's have a look at the TSP, the traveling salesperson problem. Briefly again, the definition of the problem. So we are essentially looking at a symmetric TSP where we have an undirected graph, G, without loss of generality complete, because we could add all the missing edges and give them infinite costs. So the edges of the graph have non-negative edge lengths or costs, CE, and we want to find a Hamiltonian cycle, so that's a tour visiting each of the vertices exactly once and going back to where we started, of minimum total length. The asymmetric version of the problem would be the generalization where the trip from U to V could be different from the trip length from V to U. And the first theorem says that we cannot approximate the traveling salesman problem in general at all. So the theorem is that for any constant alpha, we cannot have an alpha approximation algorithm for the symmetric TSP unless P is equal to NP. And so that's very bad news. And how do we see that? And the proof is quite simple and uses a so-called gap reduction. And let's see how we can do that. So let's assume we have an approximation algorithm A that achieves an approximation guarantee alpha. Then we define a reduction, namely from the Hamiltonian cycle problem, so the existence of a Hamiltonian cycle in a non-directed graph, to the traveling salesman problem. And that means we are mapping a graph, non-complete graph. So here we have the existence problem, existence of a Hamiltonian cycle, to a complete graph, G prime, which is going to be an instance of the traveling salesman problem. And we do so in the following way. We say, well, I mean, it's a complete graph on the same vertices, same number of vertices. And the costs for the TSP problem we define to be equal to 1 for all the edges that exist in the original graph, and equal alpha n plus 1, where n is the number of vertices of the graph, if the edge was not present in the original graph, in the instance of the Hamiltonian cycle problem. Okay, so edges that exist in G are cheap, edges that do not exist in G are extremely expensive in G prime. And okay, so then we can observe two things. First of all, if the original graph G had a Hamiltonian cycle C, we can take the same traveling salesman tour, that is exactly that Hamiltonian cycle in G prime, and each of the edges will cost 1. So that means the total cost of this tour, this traveling salesman tour, will be n. If, on the other hand, the original graph had no Hamiltonian cycle, any traveling salesman tour, which is a Hamiltonian cycle, has to use one of the non-edges of the original graph, which has cost alpha n plus 1. So that means the total length or cost of such a tour will always be strictly larger, or at least alpha n plus 1. Okay, but that means in the first case, in the case that there exists a Hamiltonian cycle in the original graph, our algorithm will compute a tour, a traveling salesman tour. Remember, it's an alpha approximation algorithm. At most, alpha times the optimum solution value. There exists a tour of length n, so at most, alpha times n. Okay, so G is the original graph, phi of G is the complete graph, the instance of the traveling salesman problem, and because there existed a Hamiltonian cycle in the original graph, the optimum solution is n, and hence the algorithm returns, being an approximation algorithm, a tour of alpha n. In the other case, since all the tours have total length or cost at least that, also our algorithm cannot compute anything better than that. So the cost of the tour that the algorithm returns will be at least alpha n plus 1, because it has to use at least one of those edges. And that is why this is called a gap reduction, because we have the following situation. For the yes instance of the Hamiltonian cycle problem, we have something smaller than alpha times n. For a no instance of the Hamiltonian cycle problem, we have a cost at least 1 larger, so at least alpha n plus 1. Okay, so we have a gap between, we have created a gap in terms of the cost function between the yes instances and the no instances. And that now means that if we assume we have this alpha approximation algorithm, which is a polynomial time algorithm, we will be able to distinguish yes and no instances of the Hamiltonian cycle problem, because the algorithm returns an objective function value at most alpha times n if and only if the original graph had a Hamiltonian cycle. And that would mean we could solve the Hamiltonian cycle problem on the original graph using our approximation algorithm, and that means we would have that P is equal to NP. So that means unless P is equal to NP, such an alpha approximation algorithm for the GSP problem cannot exist. So that is really bad news. So we have this strong inapproximability result for the general TSP problem. But there is something special in this construction that I showed. Namely, if you look at the costs that we defined, that was very specific costs. In particular, these costs on a given complete graph are not going to fulfill the triangle inequality. So they are not defining a metric. So maybe if we require these costs to be a little bit more special in that they have to define a metric, we can expect something better, and that is indeed the case. So we define the metric TSP problem to be a TSP instance where the distance function on the edges is required to be a metric. So that means it fulfills the triangle inequality. So the shortcut going directly from U to W cannot be more expensive or longer than taking the detour via another intermediate vertex V. Okay, so that's the metric TSP. Before we think about approximation algorithms for that problem, the first question should be, is this still an NP-hard problem, yes or no? Okay, so is the metric TSP problem still NP-hard? But the answer is yes. We can just use exactly the same reduction that we used before with a little modification. So we still take the Hamiltonian cycle problem here on the left-hand side, so an arbitrary undirected graph. We map it to a complete graph with the same number of vertices. And now we define the cost function just like before to be 1 if the original edge existed in the graph. So for any edge in G, the cost will be 1. For any non-edge in G, the cost will be 2, so 1 more. And that means if there exists a Hamiltonian cycle in the original graph, there will be a Hamiltonian cycle that only uses these cheap edges, so that will have a total cost of n. If, on the other hand, the original graph had no Hamiltonian cycle, we will have to use at least one of these edges. So the total cost of any traveling salesman tour, any Hamiltonian cycle in this graph G prime will then have to be at least n plus 1. So that means the decision problem now, does there exist a traveling salesman tour of cost at most n, is exactly equivalent with the existence of the Hamiltonian cycle in the original graph. So we still have a reduction from an NP-complete problem. And so the metric TSP is indeed still NP-hard. Just as a side remark, these costs now really define a metric, because if you give me 3 arbitrary vertices in the graph and you look how the cost could be distributed on the edges, however you distribute these costs 1 or 2 on these 3 edges, it will always define a metric. Okay, here is just one example. All right, so we are fine, check. The metric TSP is still NP-hard. And there is an even more special case of the metric TSP, and that is when the points are just points in the Euclidean space, in the Euclidean two-dimensional space, where the metric is just defined by taking Euclidean distances. So this is, of course, still a special case, and one can show that also this problem is an NP-hard problem. Okay. All right. So this is the overview of the situation for the TSP. So the general non-metric TSP cannot have any constant approximation algorithm unless P is equal to NP. And this is what we can get for the metric TSP. So first of all, there is a very simple 2 approximation algorithm, and that is the so-called double tree algorithm. Even nicer, there is a slightly more involved, but also still very simple 3/2 approximation algorithm. So at most 50% above the optimum minimum cost. And that's an algorithm that was published by Christofides in the 70s, the so-called tree matching algorithm. And this one really uses a lot of nice and combinatorial ideas in it in a very nice and beautiful way. And I think it's still one of the nicest approximation algorithms of all. So we can get constant approximation algorithms as soon as we restrict to the metric TSP. And for the Euclidean TSP, while I was a master's student actually in Berlin, 2 papers were published simultaneously by different authors showing that there exists a so-called PITAS, which is a polynomial time approximation scheme, which means we have a 1 plus epsilon approximation algorithm for any epsilon larger than 0. So we can come close to the optimum solution, as close as we want. So the factor, the approximation factor, will be 1 plus epsilon, and we can do so in polynomial time for any fixed and given epsilon. Okay. What I'm going to do in the rest of the lecture is explain these 2 beautiful constant approximation algorithms. And in order to do so, the first thing we have to do is to think about a good lower bound on the cost of any traveling salesman tour, so any Hamiltonian cycle in the graph. So let's see how that can be done. This is, say, an optimal solution, Hamiltonian cycle of minimum total cost. Of course, we don't know this optimal tour. Let's have a look at it and let's forget about the directions. So, and also, let us now kick out an arbitrary edge from that tour. Then what we have here is going to be a spanning tree for the graph. Okay, so let's summarize that. The optimal tour minus 1 arbitrary edge from that tour gives us some spanning tree for the graph. But that means if we compute a minimum spanning tree, the cost of that minimum spanning tree will be at most the cost of this particular spanning tree. So let's summarize that in this first theorem. The cost of a minimum spanning tree is therefore going to be a lower bound on the cost of a minimum cost Hamiltonian cycle. So that's our combinatorial lower bound, which we are going to use. The next thing that we need is we have to collect a few things about Euler tours. So what is an Euler tour in a graph? An Euler tour is a closed walk in the graph. So you start or you end where you started, but while walking along the edges, you're collecting or you are traversing each of the edges of the graph exactly once. So you can go through one and the same vertex several times, but you can only use each of the edges exactly once. And you have to exhaust all the edges. Here is a little example graph, and what would be an Euler tour on this graph? It's actually a multi-graph. It also has parallel edges, and then later on we're also going to need that. So I could, for example, start walking from V1 to V2, then down to V3, V4, V2 again, and again down to V3 and back to V1. So that would be an Euler tour, and we have passed all the edges of the graph exactly once. It was already Euler, actually in 1741, the founding father of the whole area graph theory, who proved that an Euler tour in a multigraph exists if and only if each node has even degree. Moreover, it can be found in linear time. Very simply, I will explain that in a minute. So how do I do that? How do I compute Euler tours, and why do I have this theorem here? Well, let's have a look. What I can do is I can start at an arbitrary start vertex, and I just walk along the graph in arbitrary directions, it doesn't matter, until at some point I come back to the start vertex. And I claim that this is always possible. Why is that? Well, because of the even degree condition. Suppose, for instance, you would end up here at this vertex. And now if you count the degree, you have used 3 of the incident edges. And because of the even degree condition, there must be a 4th one leaving again. Okay, so that means I can always continue because of the even degree condition And because the graph is finite, at some point in time, I will come back to the start vertex. Okay, so that always works. Now I might not have exhausted all the edges of the graph, of course. Okay, so let's assume this is the case, and our graph, that's the same example graph, still has these two red edges in the middle. But what I now have is, if I take out the edges that I was already using, I will be left with a couple of components, maybe independent components, and in each of these components, all the degrees will still be even. So it's going to be again graphs with even degree. And I can just do the same on all these components again. Okay, so here this would be just a component consisting of these two vertices and these two red edges. And indeed, I can compute an Euler tour also here by just going back and forth. And now finally, once I have all these Euler tours, I just have to glue all that together. So I have computed this Euler tour in gray, and then on this subgraph or this component, this Euler tour in red. And now I just need to glue together these tours to form an Euler tour for the complete graph. Right, so the next step would be just gluing together. And one possibility to do that would be, for instance, I start walking here, then for the first time I'm entering this component with the red edges here. So I follow the Euler tour on this component, right? And then I continue my original tour. And then I'm having glued together these two Euler tours or several Euler tours into one Euler tour for the whole graph. And all that can be done in linear time. Okay, so the even degree condition is obviously crucial for this to be possible. In any case, that is one of the ingredients, so we can compute Euler tours in multigraphs whenever all the vertices have even degree, and we can do so in polynomial time. The next ingredient that we are going to need is an argument which is known as shortcutting, and that works as follows. So there is two things that are important for this argument to work. That is the first assumption that we are talking about a metric instance of the traveling salesman problem. So that means all the triangle inequalities are fulfilled, which again means direct connections cannot be longer or more expensive than detours. And the second assumption that is important here is that we are talking about a complete graph. So all the edges are there. These two together, that's actually a quite strong restriction of all the input instances. So for instance, we couldn't say if the graph was not a complete graph, then we just add the missing edges with an infinite cost. That would create an instance which is no longer a metric instance, right? So the maximal length of the edges that we might add if there is edges missing, that is determined by the length of a shortest path. So you see, we are really talking about a restricted problem class for the traveling salesman problem when we say that is a metric instance and the graph is complete. But that's the assumption that we make, okay? Okay, so now the shortcutting argument, given these two properties of the graph, is the following. Suppose somebody gives us an Euler tour on the given graph. And here that could be the graph itself, but it might also include additional edges, maybe parallel edges. In any case, we have an Euler tour. And then the claim is that when we have such an Euler tour, ET, we can shortcut it onto a Hamiltonian cycle. So that means we can compute a Hamiltonian cycle in the same graph, which has a total length or total cost not more than that of the Euler tour with which we started. So let me try to explain that on this little example here. So here we have the same example graph and again an arbitrary Euler tour. So these labels are just numbers. So I first walk along this edge, then along this edge, then along that edge, edge number 4, 5, and edge number 6 from the Euler tour. I claim that if the graph is complete, indeed, I can shortcut this Euler tour to a Hamiltonian cycle, and that the length of the Hamiltonian cycle will be at most that of the Euler tour. with which I started. And the idea is quite simple. It goes as follows. I start walking along the Euler tour. Okay. I continue walking along the Euler tour. Nothing happens. But now for the first time, I would be visiting a vertex where I have been already. And remember that in a Hamiltonian tour, we have to visit each vertex exactly once. So I still continue walking along the Euler tour, but I'm kind of provisionally putting this edge in. Then I would continue down here. So provisionally, I would put this edge in. So this is again a vertex which I visited before. And then still I continue walking along the Euler tour. And now I'm coming back to the start vertex actually. And I have these three provisional edges. And now the claim is, because of the fact that the graph is complete and because of the fact that we have a metric instance, this direct edge from V4 to V1 cannot be longer than this detour here. That's because we have a metric. So instead of walking from V4 to V2 to V3 to V1, we take the direct edge from V4 to V1, and we insert this, and we eliminate these provisional edges, and we will have obtained a Hamiltonian cycle, which has length at most that of the Euler tour. So that would be the corresponding Hamiltonian cycle that we get. So proof by example, this always works. So whenever you give me an Euler tour on a metric and complete graph or multigraph, I can shortcut it in exactly the same way to a Hamiltonian cycle with no more total cost. Now we have all the ingredients together in order to define these two beautiful approximation algorithms. So we can compute minimum spanning trees in the graph, and that gives us a lower bound on the shortest TSP tour. We can compute Euler tours in multigraphs if they have even degree, and we can do shortcutting in order to get a Hamiltonian cycle from an Euler tour. And indeed, that's all that we need in order to describe the first algorithm. That is the so-called double tree algorithm. So the first step is we compute a minimum spanning tree in the graph. And we know that the cost or the total cost of the minimum spanning tree is at most that of any Hamiltonian cycle. So it's a lower bound on the minimum cost traveling salesman tour. Now we would like to be able to compute an Euler tour on this graph. Unfortunately, we have odd degree vertices, and we cannot compute an Euler tour on this minimum spanning tree. But what we can do in order to fix that is we just double all the edges. Okay, so then all the degrees will have been multiplied by 2. So we have a multigraph now where all the vertices have even degree. And I can compute an Euler tour on this graph in linear time, which will traverse all the edges of the graph exactly once. What is the cost of that Euler tour? Well, it's exactly twice the cost of the minimum spanning tree, and hence the cost of the Euler tour is at most twice the cost of an optimal solution for the TSP problem. And then the final step is I take this Euler tour on the graph and I use the shortcutting argument in order to get a Hamiltonian cycle at the end. And also by the shortcutting argument and by the fact that we have a metric instance, I know that the cost of this Hamiltonian cycle, the cost of this tour, can be at most that of the Euler tour, and that was at most twice the cost of the optimal solution. So we have our two approximation algorithm very simply defined. And notice that everything is polynomial time because we can compute minimum spanning trees in polynomial time. The doubling is of course simple. Computing Euler tours is a linear time, and shortcutting is also linear time in the size of the graph. Now that gives a two approximation. And as a matter of fact, this second step, this doubling step, seems a bit wasteful, right? So maybe we can improve on that. And that's what we can do. So this doubling of all the edges seems really too much, because the only problem we have to fix is actually we have to get rid of the odd degree vertices in order to be able to compute an Euler tour in the corresponding multigraph. So all that we need is a Eulerian multigraph. So that's a graph with only even degree vertices. The minimum spanning tree itself, of course, might have odd degree vertices, and the previous example showed that as well. But now the point is this. So how many odd degree vertices can this minimum spanning tree have? And here you should remember something that is called the handshake lemma. So if I count the total degrees, so if I sum up the total degrees of all the vertices of this minimum spanning tree, right, I will have counted each of the edges precisely twice, once from each endpoint. So the total sum of all degrees therefore must be an even number. It's twice the number of edges. And now I just split up this summation of all the degrees of the vertices into those that have an even degree and those that have an odd degree. Now I see that this is an even number, this is an even number, hence this must also be an even number. And therefore the number of odd degree vertices must be even, right? So this is known as the handshake lemma. In any graph, the number of odd degree vertices must be even. And the proof I just explained. And that is actually very nice because it puts us into the following position. So what we can do, I now go back to the example, and here is the 4 odd degree vertices in the minimum spanning tree. And what I can do, since we still know that we have a complete graph, right? I just pick these 4 vertices, which are now marked green, and I can compute on these 4 vertices, it's an even number, I can compute a minimum weight perfect matching on these odd degree nodes. Right, so I look at a subgraph which is defined by these 4 vertices and all the edges between them, and on this subgraph I can compute a minimum total weight perfect matching. It will be a perfect matching because the graph was complete. And because the number of vertices is even. Now this can also be done, and it can also be done in polynomial time with an extension of Edmonds matching algorithm. Okay, and now I claim the following. Now I have, first of all, it's obvious that once I add these 2 matching edges, okay, so this is the matching edge. I have 4 vertices of odd degree. I will have to add 2 additional edges to this minimum spanning tree. And as a result, I obtain a Eulerian graph where all the vertices have even degree. So again, I can compute an Euler tour on this graph, and I use the shortcutting argument to obtain a Hamiltonian cycle, which is at most as expensive as the cost of this Euler tour here. The only claim that I still have to prove is the following. I claim that the total cost of this matching that I computed in step number 2 here, that is at most half the cost of an optimal solution to the traveling salesman problem. And once I have proved that, the final tour will be the sum of the cost of the minimum spanning tree plus the cost of these matching edges. And that makes altogether at most 3/2 the cost of the TSP, optimal TSP solution. So why do I claim that the cost of this matching here that we compute in step 2 is at most 1/2 the cost of an optimal TSP solution? And that we can see by the following argument. So suppose this is the optimum solution to the traveling salesman problem. So this is the minimum cost Hamiltonian cycle. I can use the same shortcutting argument because we have a metric and a complete graph to shortcut this long tour on all the vertices of the graph onto a tour on only these green vertices, and these green vertices correspond to the odd degree vertices that we computed in our minimum spanning tree. Okay, so the length of this tour is at most the length of this whole tour. That's again the shortcutting argument. Notice that this uses edges which are not present here, but due to the shortcutting argument and the fact that we have a metric, this is still okay. This is still true. Okay, so shortcutting the minimum cost Hamiltonian cycle onto the nodes of this matching, and that, well, This is now a tour on an even number of vertices, and that will contain exactly 2 matchings, right? So on this example, that would be this matching and that matching. So this thing here is the sum of 2 matchings. Let's call them M1 and M2. Okay, so that means the sum or the sum of the costs of these 2 matchings, that is at most the cost of the traveling salesman tour. But now what we compute in step number 2 of the algorithm is some minimum cost matching on these 4 vertices, right? So that could be other edges. It could be these matching edges, for instance. But what we know is that what we compute is a minimum cost matching. So the cost of this matching that we compute, which I called M here, is at most the cost of any of these 2 matchings, M1 and M2. And that means if I now take twice the cost of the matching that we compute, each of these terms here will be cheaper than any of these 2 matchings. Okay, so twice the cost of the matching that we computed is at most as large as the sum of these 2 matchings, and we just argued that the sum of the cost of these 2 matchings is at most the cost of the traveling salesman tour. So if I look at the left-hand side, I have twice the cost of our matching that we compute in step 2 of the algorithm, and that's upper bounded by the cost of an optimal solution to the traveling salesman problem. Hence, the cost of the matching that we compute is at most 1/2 of the cost of the TSP tour. And that's exactly what I claimed. So that finishes the proof and finishes, say, the final argument on this beautiful approximation algorithm by Christofides from the 70s. And the nice thing about this algorithm, if I go back to the description of the algorithm, is really that we need a whole bunch of combinatorial arguments and algorithms that we also derived in this course. It's computation of a minimum spanning tree. It's computation of matchings, minimum cost matchings. It's this shortcutting argument. We need the handshake lemma in order to know that there exists a perfect matching on these odd degree vertices. So we really need a lot of these combinatorial and beautiful arguments to make all that happen. Anyway, so that finishes lecture number 11. So we are almost on the finish line, and the final lecture will contain even more classics and beautiful stuff from approximation algorithms. And for the moment, I thank you for your attention, and I hope you enjoyed, in particular, this last approximation algorithms. So see you back for lecture number 12.